Welcome everyone. So today we'll have a Roman from UCLA to tell us about Heegaard Floer's symplectic cohomology and the generalized Viterbo isomorphisms.
Um, Thank you very much. Thank you for having me. It's nice to be virtually at Minnesota. Um, so today I'm gonna tell about Heegaard Floer symplectic homology and generalized Viterbo isomorphism. All I'm going to tell is a joint work with Tianyu Yuan, and I'll start by reminding what these and these parts of the title mean. Please don't hesitate to stop me with any questions. I hope, well, at least first 20 minutes should be accessible to a broader audience. So here is the setup. We start with a Liouville domain M of dimension 2n, and let's say lambda is a one form such that omega, which is equal to d lambda, is a symplectic form. So usually lambda is called the primitive of the omega, and we think of this Liouville domain as of a manifold with boundary. So there is it has contact boundary GM, and we attach to it symplectization end to get a completion. So completion of M is the following construction. So here dm is this contact boundary, and we attach these portion here, which is usually called symplectization, and this is simply the product of this contact boundary with array, and we extend this one form to this symplectization end by just setting it to be equal to the restriction of this lambda here to the boundary times r. So at the boundary, when r is equal to 1, it indeed coincides with just lambda restricted to dm, and then it scales. Okay, so now to define symplectic homology, I mean, for the chain complex, the generators correspond to orbits, to closed orbits of some Hamiltonian vector fields. So I need to set up some set of functions. So we say that H is in this set of quadratic ad infinity functions if, well, first the function is smooth, and second, h of Rm is equal to 1/2 R squared for R bigger, much bigger than 1, and well, M is some point in the boundary here. So we basically require that, well, maybe on some compact portion of the completion. So it's actually a function on the completion. Maybe on some compact portion, we allow any sort of behavior, but as we approach this ideal boundary, it is required that function behaves quadratically. We additionally consider some now time-dependent. So these are quotient z is a time parameter. So you think of this as S1. So this is again a smooth function f and absolutely bounded. So this f serves as a perturbation, and I could start with the Hamiltonian vector field of H and its orbits, but then there is a problem. Any such orbit, since H is not time dependent, would be like you would get S1 symmetry of orbits, and you would be in such Morse bar situation. So to break this symmetry, we introduce this function f, and then O would be the set of time one closed Hamiltonian orbits of the total Hamiltonian H dot, which is equal to H plus F. So now this Hamiltonian H dot is sort of time dependent Hamiltonian, and well, H can be thought as such just by putting it to be equal to this H for any time parameter. But since we added this perturbation, now this H dot is not time dependent. So any closed orbit, it will have a fixed starting point, and we cannot like just rotate a bit and get to the same orbit because of this time dependent parameter. We can always make sure that all such orbits are nice, and so well, they're non-degenerate, whatever that means. And then the symplectic cohomology, just as a like symplectic cochains, just as a module, is set to be equal to Q and generated by this set O. So this is as a just a Q module. And to add gradient here, we said for X in O, we assign gradient to be equal to n minus Conley-Zedler index of X. And well, this is some classical quantity. And now, well, with this, I can say that this is actually a graded Q module. So now we have a structure of graded module, and to make it into a chain complex or a DG module, we only need to introduce the differential. So the differential is then for any such generator X is given by counting cylinders connecting X to any other orbit X prime, such that the difference between the gradients is equal to 1, and U is some curve here in the moduli space of cylinders connecting these 2 points. So more explicitly, this moduli space is a space of maps from a cylinder to our completion, connecting X and X prime. And when I say connecting, it means, so this is how you can think of it. This cylinder is sitting somewhere inside Rm hat, and at plus infinity, so when this coordinate goes to plus infinity, it should limit to the closed orbit X, and when it goes to minus infinity, it should limit to X prime. And well, by some general theory, we know that when the difference between these gradients is 1, the moduli space has dimension 1, so there are finitely many points in here. And here I write it as dux because there is also some sign involved, but I'm not gonna say much about it unless you ask me. But just to make sure, if you want to define things, say over Q or over Z, then we need to care about signs, but they come with orientations. And then it is important to say that this has to be like J holomorphic curve. So it's not any map. It's some J homomorphic with respect to some J. So there is a choice of almost complex structure on M hat, and this almost complex structure is supposed to be something called contact type at infinity, or a scaled contact type, but maybe I won't go into these details. And I'll just say that the claim is that the cohomology of this complex is actually an invariant of M up to Liouville isomorphism. And that means that it actually doesn't depend on H and J, and moreover, it doesn't depend on this completion that we chose, because there like for like symplectomorphic Liouville domains, there could be like different completions, but it has been taken care of by this fact that this isomorphism is still with respect to Liouville isomorphisms. So it is a genuine invariant of a Liouville domain M. It's been first introduced by Viterbo by slightly different construction, but essentially equivalent, using some direct limit constructions. Well, this invariant over the time proved to be quite useful in various applications. And the first interesting computation of this invariant comes when you set your Liouville domain to be cotangent bundle, or say unit sphere bundle as initial M, and then the cotangent bundle is M hat, or like unit disk bundle, sorry. So the theorem, which is known as Viterbo isomorphism theorem, and I attribute it here to many people, including Abundando, Schwarz, and Abuzait, because, well, it had some history, and the statement that I'm going to write is, I guess, finally due to Abuzait, and there are known several proofs. So symplectic homology, twisted by some background class B here that I write, is isomorphic to the homology of the loop space of the zero section. So let's say for any closed oriented manifold Q, where B is a certain background class. Maybe I'll say more closer to the end about this background class, but yeah, it's kind of important that there should be a twist.
May I have a question? May I have a question of your definition of the differential, the x and the x prime? So since your manifold is a newer manifold, is non-compact, so I'm thinking your x and the x prime, do they have to live in the compact part of your manifold, or they can also sit in infinity like a simple field theory in the asymptotic?
Right, so yes, so here is the thing. They don't leave it like at super infinity, but then there is definitely a reasonable question. What if in the limiting procedure we go to infinity, and then there is a sort of maximum principle holding here in this particular setting, because because of the exactness and because of the choice of the function to be quadratic at infinity, one can still show that there are no breakings. So you don't need to split the target. And this is this is sort of this is very important for these things to work out. So so yeah, this maximal principle, I guess, is initially to Seidel and Abuzait, and in a symplectic homology setting, it is like they worked out in a Lagrangian setting. In symplectic homology setting, it's worked out by Ganatre in his thesis. Yeah, but that's definitely a big issue for the compactness arguments. Yeah. So yeah.
So the reason you have a single chain complex computing symplectic cohomology rather than taking direct limit is also due to you choose the quadratic Hamiltonian.
Yes, exactly. So you can also work with linear Hamiltonians and get this direct limit definition, but turns out it is isomorphic to the definition for the quadratic Hamiltonian. We actually will work. I mean, we work in both settings, but I probably prefer the quadratic setting.
Okay.
But yeah, let's say if you actually want to prove this theorem that the invariance with the limiting construction is much easier because you just say it is a limit over all linear functions, and then well you basically get invariance for free more or less because of how nice limit is for this quadratic function. I guess the proof goes that you just show it is equivalent to the limit definition. And actually, if one would want to show invariance for the quadratic definition, it would be, I'm not sure if it's written anywhere. Maybe a reader knows how to write it down, but it would be hard. So yeah, limit definition is definitely important in this picture. Okay, yeah, thank you, and thank you for all these questions. Yes, so so maybe to comment on this result, yeah. So I guess the existence of the fact that one needs to twist by this background class was not obvious at the time of Viterbo, and I guess it was first noted by Thomas Krach for the example of CP2. Then it was fixed, and actually there is a result in a non-orientable case as well, but then one has to twist a bit more by some local system. And okay, I'm not gonna talk more about that. And okay, now I guess we have some understanding of symplectic homology. So let me speak about Heegaard Floer. Now, so this, okay, I'm sure there are many experts here on Heegaard Floer, so I'll rather give some perspective on it than tell you what it is in a sense which is more relevant to what we are doing here. So first of all, one has to mention that Heegaard Floer were introduced by Ozet and Jabba and Jacob Rasmussen independently as invariants of three manifolds or links in three manifolds associated with counts of J holomorphic curves in a symmetric product of a surface, which is a surface in which one draws a Heegaard diagram of a free manifold. And I guess in what I wrote, the most important part for me is the last one. That's what we are that's what we want to do basically. We want to get some invariance of something obtained by counting some J holomorphic curves in a symmetric product. Why there is a big difference between, say, the case of a surface and any other higher dimensional case, because symmetric product of a Riemann surface is actually a very nice smooth manifold. Unlike, and this doesn't hold true in general. In general, symmetric product is just some orbifold. And if one wants to count curves there, well, there are certain complications arising with it. Well, the next more recent work, which gives more like closer perspective the way I think about it is a quantitative Heegaard Floer homology introduced by Christopher Gardner, Vincent Humilier, Check-U-Mock, Sobhan Zeffadini, and Ivan Smith. This is now an invariant of sigma itself regarded as a symplectic manifold, and it also given by counts of curves in the symmetric product, and they used it to show well, I would rather say to resolve long-standing simplicity conjecture. And well, this was for maybe 40 years unknown. The answer to this was known. It was an important problem in C0 symplectic dynamics. And coming back to the original Heegaard Floer invariant, there is another perspective which is also used in this work, but I guess initially goes back to the work of Robert Lipschitz, who gave cylindrical reformulation of the original HF by counting curves. Now, instead of symmetric product, it turns out you can count curves in the product of initial sigma with a strip. So this is just a strip, and with a requirement that projection to the strip of U has to be a k-fold branched cover. So it turns out that studying curves, at least in the case of two-dimensional surface in here, is equivalent to studying such maps in this just four-dimensional space, not like 2K dimensional space, with this requirement that the projection is a k-fold branch cover. And well, the main like kind of instrument between these two is the so-called tautological correspondence. Okay, tautological correspondence. I guess it's initially was brought to symplectic geometry by Evan Smith, and it is also, this perspective is also being used quite heavily in this work. Well, something that I didn't write, but I'll just say, there are also works in direction, well, what if we go just one dimension higher? Instead of Riemann surface, we take a complex curve. And there are works by Seidel and Smith and Abzade and Smith and Manolescu in defining symplectic Hovanov homology, and those are given by counts of curves in a Hilbert scheme of a certain complex surface. And Hilbert scheme can be regarded as a desingularization of the symmetric product in this case. And luckily in this real dimension 4, in case of complex surface, we can do this resolution of singularities and work with Hilbert schemes. And this kind of saves us from, well, saves them from working with some orbifold and homomorphic curves counts. But going in to like arbitrary dimension, there is still, well, there is no known good way to desingularize things unless you just explicitly say, let's work in this reformulation by Robert Lipschitz. Maybe it doesn't give you exactly what the counts in the symmetric product would give you, but it gives you something. And recently, Colin, Honda, and Tian introduced higher dimensional Heegaard Floer homology by counting curves in the product of a strip with the completion of a Liouville domain. So all these invariants now are actually just incarnations of Lagrangian Floer homology in this symmetric product setting. And maybe the question for my project is like, what is a proper invariant, which is an analog of symplectic homology in this symmetric product setting, maybe applying this cylindrical reformulation. And that's what we are going to do. And maybe, well, I'll end this perspective by this slogan, Heegaard Floer without Heegaard diagram. Many such cases. So now maybe people who love original Heegaard Floer would appreciate this other perspective as well. Okay, now coming back to what we are trying to do. So we are trying to model using this cylindrical perspective, the symplectic homology of symmetric product. So now by the analogy with what we saw in the very beginning, we need to set some generators. So they are supposed to be closed orbits in a symmetric product. Now, before going into some actual definitions, what is the point in the symmetric product? The point in the symmetric product is just a k tuple of points, and these points start moving around in space, and then they come back in the position from which we started, but they probably can permute, and so we can think of them as some identical particles. And after time one, we cannot tell whether, like, if they permuted, whether something happens. So we should count this as a closed orbit. So, but to get a setup, we still need to do some desymmetrization. So we start with the quadratic at infinity Hamiltonian as before, and we pick some perturbation of that. And now to adjust for the fact that we have these k particles, we introduce k small perturbations of f naught, maybe satisfying some more properties to make sure that everything that I'm gonna say further works fine, but let's ignore maybe these details for now. And then we set as our generators the set of Hamiltonian k multi-orbits of certain type for a given permutation in a group sigma k of permutations on k elements by being just the set of k tuples of Hamiltonian paths. So xi, each xi is a path in M hat such that xi dot is equal to the Hamiltonian vector corresponding to ith total function. And well, this ith total function here would be just the sum of initial h naught with this perturbed f0, basically this fi. And second, x, so this is one condition. The second condition is that these paths actually form these multi-orbits of the prescribed permutation type. So the end of xi path should be the start of sigma of I paths for for these sigmas here. And now the whole set of these K multi-orbits is just the disjoint union of this P sigma over all sigma in a group of permutations. Now let me show this example. Let's assume we pick sigma in sigma 5 being just a cycle permuting 3, 4, and 5, and 1 and 2 stay the same. So that means that the first particle, now we kind of desymmetrize, but we still want to get this picture of 5 multi-orbit. So these two particles, they just should come back to their own place. But now these 3 particles, they are allowed to permute in this cycle. And this path should go along this third Hamiltonian vector field, these along the fourth, and so on. So these are our generators. Now, there is a Z gradient as before, and the formula for the K tuple would be equal to K times N minus X C1 of sigma minus etc. minus X CL of sigma. And well, you probably guessed from the previous picture that each such orbit, given sigma, you can decompose it into a bunch of orbits. So for instance, you can think of this as 2 times 1 orbits and 1 times 3 orbit. So this decomposition comes in accordance with the cycle type of our permutation. So we decompose our permutation into the product of cycles C1 of sigma and then CL of sigma, and L of sigma is just the length of sigma with respect to this cyclic type decomposition. So these are all cycles. And for each one of them, oh, I'm sorry. This was supposed to be Conley-Zander index. So we subtract as before Conley-Zander indices of these orbits. And it doesn't really matter that they are of longer time, we still can assign Conley-Zander index. Okay, so now we can first form our trivial complex, which is as a graded Q module as is just the module generated by this K multi orbits. So this is Q graded module. And now we need to introduce some differentials. So if we can think of this tuple as, say, a tensor product of these corresponding cycles. And essentially, one can think of these trivial complex that we just got as, well, in some sense, it's just a semi-direct product of sigma K and the original chain co-chain complex for the symplectic homology. So, well, this is just the way to think about it. And then the differential on the tensor product, you can set it to be the sum of X C1 of sigma tensor, blah, 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 tensor, the original symplectic co-chain differential on the corresponding orbit here, and then blah, 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 X CL sigma. And pictorially, one may think of this as a K-fold cover of a cylinder, but with like the pre-image surface being just a bunch of cylinders. So it's like K cylinders, and these cylinders corresponding to, say, XC1 of sigma and so on, they're just trivial index 0 cylinders, so nothing is happening there. But this is the cylinder that we actually, well, counted, and there could be some, like, this is our XCI of sigma, Now, here could be some x prime, some interest in orbit, but this is not like why we're gathered here. We wanted to get all k-fold covers. So adding all k-fold covers, I would be thinking of this as a deformation problem for this trivial complex. So let's me spend some time explaining what this deformation problem here is. Let n be this QDG module, and you can think of this as a chain, as just a chain complex. And we ask ourselves, what are the deformations of n for some reason, maybe, well, I'll explain it later, with a parameter of gradient 2 minus n. So in case 2 equals n, it would be just the standard deformation problem, and you should get some power series, maybe some differentials of higher powers, but like in like other cases for other n, well, you should think a little bit more. Let's put it this way. So let's start with the first order deformation. As a just QDG module, it is supposed to be just a tensor with dual numbers in H as now QDG module. Sorry, as a Q just graded module. And this is a tensor product over Q. So you can write this as our old n, which is n0, plus h times n0. So now we need to introduce a differential here, and differential would be some old d naught, which existed on n naught. So n naught is equal to n. And now we need to add d1h to this. And this d1h would be going from here to here. And well, here it would just be 0 because we set h squared to be equal to 0. Well, now the full deformation is obtained by just standard inverse limit construction. So, well, you start from somewhere there, and then you have n3, n2, n1, and then it goes to n0. So say n3 would be equal to, as just a QDG module, as a tensor product with Q of H quotiented by H to the power 4. And so together like this, D3 would contain D1H, D2H squared, and D3H squared. So the full complex, so like the full complex, this, which can be obtained by some direct product construction, will contain this full differential, which is unfortunately not a power series, but can be thought of as a power series. So in particular for our HFSH complex, we think of this as a complete deformation of the trivial one. And on the nose, you can set it as a direct product of this form. Let me just write it. So here you take this K-trivial complex that we defined before, and you add degree shifts, or equivalently, this can be thought as multiplying by h to the power j. And a differential here would be this, like, not exactly the sum, but I'll allow myself to write it like this. So this would be this like infinite sum, and it would be going, well, I mean, you would be starting from something like this, and it would be going to all possible direct shifts. So together with so this is our trivial differential. Now I'm saying that to get the differential that I'm going to introduce, I need to introduce D1, D2, etc. And they would correspond to this degree shifts. Maybe a remark here that this deformation setup is parallel to the SFT generating function by Ellie Ashberg, Giventhal-Hofer in their propaganda paper. And one may also think about this invariant that I'm going to introduce in a moment as a with respect to this trivial symplectic cohomology. The relation is the same as between full SFT and rational SFT. Okay, so now without going any further, let me introduce this invariant. So the moduli space, which would be involved in the counts, would be the moduli space of maps from some Riemannian surface to the product of M hat with a cylinder. Well, such that, well, first condition, well, first U is equal to the pair pi V, and pi is a projection to the cylinder, and pi is supposed to be a k-fold cover of the cylinder. Well, second, this curve, like the projection to M hat, should satisfy perturbed d bar equation, and perturbed by certain, oh, sorry, maybe let me write it just like this: x h s pi pi star of dt 0, 1 equals 0 with respect to a certain j s pi. So here I want to comment on these indices. It means that there will be some Floer data on the space where s and pi leave, and we'll make sure that this is a nice Hamiltonian data and corresponds to the fact that we want at the limits to limit to our Hamiltonian k tuples of orbits. And here these x and x prime are the tuples. So they're actually like on S, there is a bunch of punctures. So let me look at actually these pictures. So this is our S and this is pi. So we want, say in this case, this is a four-fold cover. And at each end, we want to say that these, here we would be limiting to the first orbit, which is a time 2 orbit. Here we want to limit to the second time 2 orbit. Here it will correspond to the time 3 orbit, and here to a time 1 orbit. So I'll roughly say it as like limit as z goes to some puncture pi plus should be equal to x ci of sigma, and limit as we go to some puncture pj minus should be equal of v should be equal to x c cj prime of sigma prime. Okay, so this is what we want now, and this is like the idea of what we want to construct, but like there are certain challenges. First, people usually use the Deligne-Mumford space to model space of solutions to J-homomorphic curves. And if you just think about it for a moment, in Deligne-Mumford, for an element of a Deligne-Mumford, you say no that it has some puncture, but puncture doesn't tell you whether you are going to the 2-time orbit or to a 3-time orbit. Without the data of this map to pi, you don't know the multiplicity at each corresponding end. Second, what we really want from our Hamiltonian data is that near the ends, we have these asymptotic markers. And here it will be, say, H1 on this portion, and then H4, and it will extend to this to this neighborhood, in this neighborhood, it will look like H1, H4. Maybe we allow something to happen in the middle, but near the ends, it should look exactly like those Hamiltonians that we want to see there. And well, the same here. It should be H2, then H3, and the same for the ends, for the negative ends. So we want these kind of behavior, and because of this, so like, okay, this is first challenge, limiting behavior. Let's say at the end, but much bigger challenge is, well, compactness issues.
Roman, could you remind me again? What's df? In the pipe, go back df. What's df?
Oh, df. Sorry.
Yeah.
This is dt. Yeah. Thank you.
I
Yeah. I mean standard coordinates
Okay, I see.
st here. So this is going to be the pullback of dt form here. Yeah, thank you. And that's an important question. Yeah. So like, and on the cylindrical portions, it will be just the standard dt, but at the branch points, yeah, let me mark. So in this picture, there are 4 branch points, and near the branch points, it will actually just be 0. So near the branch points, the map is just like J holomorphic. Yeah, thank you. So the most important problem is like compactness issues, because, well, as we know, if you go to the limit in this SFT type picture, there is a possibility that multiple covered curves can occur. And, well, our goal is to cure this with the fact that we're limiting to this ends where there are prescribed Hamiltonians, and we can make sure that for different tuples of Hamiltonians, we have orbits sitting far away, and they're not symmetric, so that we are trying to assure that that there is no multiple covered curves. But this is definitely an issue. And, well, the solution sort of that we propose is to use the Hurwitz space instead of the Lee-Mumford space, and maybe some upgrade of this space. So let me just say what this space is. So given 2 permutations and an earlier characteristic, we set H sigma prime k and chi is the moduli space of k covers like this. And, well, here is a picture of an element in, say, HID and transposition of 1, 2. The Euler characteristic just corresponds to the number of branch points, and k is equal to 2 in this picture. So this is an element there. And we quotient out by holomorphisms on S. So this is our S, and this is a target. And, well, there is some markers data that we want to keep track of to assign Hamiltonians. So biholomorphisms should respect this, but we don't quotient out the action on the target. So the Hurwitz space, well, we will only quotient out the vertical action. So we set the Hurwitz space to be the quotient of this H tilde by the vertical action on the target. So these parallel transports. And the difference between this Hurwitz space and the original Hurwitz scheme, which was known, I guess, back to Hurwitz, but definitely to Fulton, is the quotient of this same space, but by the full action of R times S1. but we don't want to quotient out S1 since we don't have S1 symmetry, and this will be helpful for us. So now we can perfectly assign all the Hamiltonian Floer data so that the behavior near the ends is fine, because now just from the data of the cover, we know the multiplicities near the punctures. But what we don't know is what happens when we go to the boundary. So there is a Harris-Mumford compactification for the Hurwitz scheme, and it's different a bit from the stable compactification because, well, in the stable compactification, we just allow bubbles on our map, but we don't do anything to the target. But here we'll add actually bubbles on the target. So if, say, you have such cover and some sequence where these two branch points, they come together, well, we have some problem in the solution, which was proposed by Harris and Mumford, is to add a bubble here, which would contain these two branch points. Well, I'm not going to draw the pre-image of this double cover, but I guess it's more or less clear what it should be. And this is what happens when 2 points go close to each other, but when they go far apart from each other, well, we should see our familiar from SFT picture two-level building like this. And it corresponds to these two cylinders breaking apart and having two branch points. So this is how this compactification works. And due to EONL, there are nice coordinates near the boundary. So when let's consider only this second type of the boundary, which is like smooth breaking, and this is bubbling that we plan to show that they are not happening. So this is a smooth two-level breaking. We have these markers at -infinity and +infinity, which correspond to, say, direction 1. And since we didn't quotient out S1, we actually can say that this is equal to 1. But usually one sets the coordinate in the gluing of of a nodal curve as an element in C, maybe up to some translations here, but not up to rotation. Well, maybe up to rotation, but we don't need to quotient out rotations. And then there are same parameters here, and maybe, I don't know, this is some psi L. And in theory, one could think, okay, we can probably allow any size in the domain, and we will still have some branch covers. But turns out to make sure that you get a branch cover, if there are multiplicities mu1, mu2, mu-L, so these are the multiplicities with which we map on each particular end, on each particular node here, they should satisfy the following equation. So it should be actually these CIs are defined by this data here as well to a finite collection of solutions, and this is an equation that should be satisfied. So that means that Harris-Mumford compactification actually, well, it's not smooth, but it gives as an orbifold, and like near the boundary there are mu1 times mu2 times mu-L sheets. So this is like the only problem we have. And to treat this problem, we introduce on this compactification sort of branch manifold structure. So what is that? Well, let me show this picture, and after that, we'll have all the ingredients. So let's consider this moduli space. So this is a generic fiber in this space. And there are these two types of boundaries, right? We can break, say, this way or this way. Now, the problem that we have, okay, so if we choose this data to be equal to 1, then in each break-in, we can assign this matching data. So if we keep track of these matching data, then we actually get a full resolution of this moduli space. So if we add in the boundary this matchings data, which correspond to just choosing one of the like mu1 roots of unity, then we will know how to like match these points here. But unfortunately, it still leaves us with two options where we say that this is the first puncture and this is the second, versus where this is the second and this is the first. And same thing here. We don't know what numbers to assign. So we don't know which Hamiltonians to write there. So to fix this, we'll actually replace the neighborhoods with two sheets, each with weight 1/2. So the actual solution when projected to the Hurwitz space would look like something like, well, here it would be a nice curve, but then it will branch into two curves. And then there'll be 2 points on the boundary, and the same here. And they will come in with weights 1/2. So that's sort of the idea. And here I'm ready to state the main theorem. So if you model on this Hurwitz branch manifold, the space of your solutions, that then will be the weighted non-singular branched groupoid of dimension n-2 times chi plus x prime minus x, their indices -1. And this n-2 here actually explains why we have this gradient parameter. And for dimension less or equal than 2, it admits compactification. And when the dimension is exactly to the boundary, it looks like this. So and weight is 1 over k factorial. So knowing that, we now can show that d squared is equal to 0, and this is sort of the main challenge. And the di is then, so the full differential now can be said to be equal to this, where di is the count of curves in mk minus I x prime. And then the theorem we show states that, well, the symplectic homology is actually is an invariant of M up to Liouville isomorphism. And I'm sort of running, well, I'm out of time, so I'll just say one word. So we actually then wanted to compute it in the case of cotangent bundles, and we introduced some Morse model, and we showed that this symplectic homology, well, there is a map from symplectic homology of cotangent bundles to this Morse model that unfortunately I didn't have time to explain, of certain loop space associated with the symmetric product, which is a quasi isomorphism when Q is smooth orientable, well, closed manifold with a second Stiefel-Whitney class of TQ equal to 0 in the second cohomology of cotangent bundle. And okay, I guess I'll stop here. And this is the picture for the map. But yeah, I guess I'll stop here.
Thanks.
Okay, question. So what's the role played by your small perturbation H1 till HK is small F1 till FK?
Right.